Hello my dear students. Today we will be discussing the different types of load torques. So let us study each type of load torques. So mainly there are two types of load torques. One is the active load torque, another is the passive load torque. So the first type of load torque is the passive load torque. So what is the example of a passive load torque? Say frictional load torque. It is a passive load torque. So they exist in all motor load drive systems simultaneously. In most cases, only one or two are dominating. So this frictional torque exists when there is motion, because in practical cases, the frictional force is always there. When I try to move, the friction is opposing me. When a car tries to move, it is opposed by the frictional force. When a train tries to move, it is opposed by a frictional force. So in practical scenario, friction is always there. So now there are three types of friction. One is the Coulomb friction, the second is viscous friction, and the third one is friction due to turbulent flow. So the line represented by green, it is known as Coulomb friction. So you see that the torque is constant throughout the speed. The frictional torque tau c due to Coulomb friction, it is equal to constant, whereas the torque due to turbulent flow, it is proportional to square of the speed, whereas the torque due to viscous friction, that is proportional to the speed. So it is a linear. So the resultant of all three is superimposition of all these three types of torques. So the frictional torque is equal to function of Tc, Tf and Tv. Now the example of an active load torque, that was passive load torque, that is the gravitational load torque. It is the type of a active load torque. And you see again, like Coulomb friction, it is also constant. With speed, it is also constant. So let us take the example of an inclined plane. So in an inclined plane, let there be a vehicle drive. So now the load torque is try to move in the downward direction, while the electromagnetic torque is moving in the upward direction. So the motor is generating, coupled to the wheels, it is generating electromagnetic torque. So it should be in the clockwise direction, where the load torque should be in the anti-clockwise direction. So now if the mass of the system is m, so the vertical downwards force, it is mg. So now if this angle is alpha, so this particular force, it is mg sin alpha, and this force is mg cos alpha. So this is a gravitational drive. Now this is the example of a hoist drive. So you see, this is the characteristics. First the torque decreases with speed, and then again it increases. So the next is the load and the motor at steady state torque. So at constant speed, so what was the equation? T is equal to TL plus J d omega m dt. So this is the first order ODE. So if omega m is constant, this will be 0. ddt of a constant is 0. So T is equal to TL. So suppose let this be the load torque profile, and the electromagnetic torque is like this. So at here, when they intersect with each other, the values become numerical same. So it is known as steady speed. So at here, TE is equal to TL. So this is the example of a numerical problem. So a torque profile has been given over here. So you see, this is the time of 60 milliseconds, and here at 10 millisecond the torque is increasing, the speed is increasing, and the maximum speed is 100 radian per second. It stays constant for 20 seconds. From 25 to 45 it's 20 seconds, and then it falls down to 60 seconds and becomes 0. So what you are asked to calculate is the net torque. So what will be the net torque produced? The system, there is an equation given over here, that TE minus TL is equal to J d omega m dt plus BW. That means this thing they have considered. So this is what? This is the viscous friction. So the value of B is given over here. The value of J is given. The load torque value is given. So now let us try to solve this thing. So from 0 to 10 milliseconds, from 0 to 10 milliseconds, what will be the electromagnetic torque? Substitute in this particular equation. J is 0.01, and what is d omega m dt? Omega is 0 over here, so derivative is 0, plus B is 0.01 into omega. Omega value is again 0 over here, plus 5. The load torque is 5. So this thing and this thing becomes 0. So it is 5 Newton meter from 0 to 10 milliseconds. So now this is complete. Now let us consider this duration from 10 to 25. So now TE, that is equal to 0.01 into 100 by 0.015. So what is the time interval? The time interval is 15 milliseconds. So in terms of seconds it will be 0.015. And what is the change? What is the change in speed? It becomes from 0 to 100. So 100 minus 0 by 0.015 plus 0.01 into here, what is happening? It is B into omega plus 5. So the value of omega is given. So the value of omega is this. Now from 25 to 45 milliseconds, T is equal to 0.01 into 0 plus 0.01 into 100. So it will be identical as this. plus 5, that is equal to 6 Newton meter. So where is the difference? The difference is in the omega. So from here to here, 25 to 45, omega is 100. So you substitute 100 over here. So it is 6 Newton meter. Now again, here from 45 to 60, that means for this interval this is completed. So here, so it will just be the opposite. So it is 0.01 into, just substitute minus over here, minus 100 by 0.015 plus 0.01, and it is 400 minus 6666.67 T. Plus 5. So this is the equation. So now different types of numericals are given over here. So this is one type. This is the torque profile. So corresponding to this speed profile, this is the torque profile. Now for the same system, if this is given, you derive the speed and the torque profile. This is left as an assignment to you. You just solve this assignment and you get back to me for any questions. Now let us consider the speed torque characteristics. So now there are two regions. One is the constant torque region, tau is equal to constant. Another is the constant power region, power is equal to constant. So now if we plot the torque versus power, torque power versus speed characteristics, in the y-axis we represent the torque and in the x-axis we represent the speed or the frequency. Then for constant torque region, obviously this will be a flat line, it will be constant. So this is the torque, this is the torque. So torque is constant over here, and this is up to the base speed. So after the base speed, what will happen? It will fall. Like this. So now the torque is reducing. And here you see the power is represented by the dotted line. So here if the torque is reducing, the speed will be increasing now. So torque is reducing, and above the base speed the speed is increasing. So power is equal to constant. So this region is the constant power region. So power here is constant, but before the base speed the torque was constant and the power was increasing. As because omega is increasing. So this point is the tau rated. This is the rated torque. And this is P rated. So there are two zones of operation. One is the constant torque zone and another is the constant power zone. So load torques can be classified into broad categories. One is the active load torque and another is the passive load torque. So the load torques which has the potential to drive the motor under equilibrium conditions are called active load torques. So the motor under equilibrium condition, this is very important. So under equilibrium condition, active load torques is able to drive the motor. Example, the torque due to force of gravity. This is active load torque. Torque due to tension. So the load torques which always oppose the motion and change the sign on the reversal of motion are called passive load torques. So which opposes the motion, they are known as passive load torques, and which aids the motion are called active load torques. So passive load torques are torque due to friction, cutting, etc. So the load torque tau L can be further divided into the following components. One is the frictional torque. So friction will be present at the motor shaft and in also various parts of the load. So the frictional torque is the equivalent value of the various frictional torques referred to the motor and the shaft. So that was shown in the diagram, represented by three different colors. Another type is the windage torque. So when the motor runs, wind generates a torque opposing the motion, that is known as windage torque. So torque required to do the useful mechanical work. Nature of the torque depends upon the particular application. So it is very much application dependent. So it may be some function of speed, it may be time invariant or time variant. So torque, load torque may be time variant or it may be time invariant, it may be a function of speed. So its nature may also change with the load's mode of operation. So the load demand is also very important. So the frictional torque can be resolved into three components. So number one, the viscous friction. So it is denoted by tau V. It is equal to B omega. So if we draw the graph, this we have already shown. So tau V versus omega, that will be a straight line. Another component which is independent of speed, it is known as tau C. So if you draw tau C in the y-axis versus omega, it will be constant. The third component is tau S. For additional torque present at standstill, this tau S is present only at standstill. It is not taken into account while the dynamic analysis. So dynamics means motion. So standstill torque will not accountable in dynamics. Another is the windage torque, that is proportional to the square of the speed, which is given by tau W proportional to omega m square. So if we plot tau versus omega, it will be like this. So the nature of the load torque depends upon the particular application. A low speed hoist is an example of the load when the torque is constant and independent of speed. At low speeds the windage torque is negligible, therefore net torque is mainly due to gravity, which is constant and independent of the speed. There are drives where Coulomb friction dominates over the other torque components. Consequently, the torque is independent of speed. Example, paper mill drive, fans, compressors, aeroplanes, centrifugal pumps, ship propellers, high-speed hoists. Traction are the example of the case where load torque is the function of speed. So in most cases it is the function of speed for high-speed hoists. So we will stop over here for today. Thank you.